We're asked to find the resistance of a 40 watt light bulb with a 120 volts in it. So when we're given watts, instinctively you should be thinking about power, because power relates to wattage, right? Because whenever you have a utility bill, they send you a bill that charges you for the amount of power that you use, right? And usually those are in kilowatts. So whenever you think of power, or whenever you think of watts, think power, okay? So P is equal to 40. Okay. So whenever you're thinking about power, these equations should be popping up in your head. P is equal to the ampage, the amps, times what? Voltage. And this is what we're going to mainly use for this problem, but if you want the other equations, it's P is equal to I squared times R, alright? And we can derive the other one. Okay, so we're asked to find resistance, which is R. How do we find that? Well, if you have voltage and you have power, but you need what? Amps. How do we get amps? What relates amps? Well, think of this. Think of Ohm's law, that R is equal to V over I. Okay? If we solve for I, we get I is equal to V divided by R. So let's plug that into this equation. Alright, so P is equal to, we're going to say I is V over R, and we're going to multiply it. We're going to multiply it by V, right? This came over here. Therefore, we have that P is equal to V times V, right? Because it's the same thing as saying V times V over R, okay? So we're just going to have V squared over R. Okay, so now we have to solve for the resistance. A simple algebraic trick is just to swap the P with the R and just swap the R with the P. Alright, so we end up getting R is equal to V squared over P. V is just the volts, and we're going to do this in a different color. So this gives us 120. We're going to square that, and then divide that by 40. And let's see here, what do we have? 120 squared divided by 40 should give you 360, and it's ohms. So the trick here was that you have to know that whenever you see power, or whenever you see wattage, you're going to think of power. And whenever you think of power, you're mainly going to be using this equation, that power is equal to the amp times the voltage. And it's always useful just to write this down. Like if you have wattage, just write this down regardless, that the resistance is equal to the voltage divided by the amps. And so to solve this problem, I needed to find my amp. And solving for my ampage, I get V divided by R. And so I'm going to resubstitute that into my I value. And we now have V times V, which is V squared divided by R. We're going to be solving for R, so we're just going to swap R and P. So 120 volts divided by 40 watts is 360. Just remember these two equations, and you can use them to solve a lot of the problems. Alright, so in this question we have two particles that are separated by half a meter. One particle is 0.05 kilograms, the other one is 0.02 kilograms. One of them has a charge of 5 microcoulombs, and the other one has a charge of negative 20 microcoulombs. We're asked to find the magnitude and direction of this particle. Okay, well, the first part is pretty simple. We're asked to find the direction, right? Well, the direction is that Since this is a positive charge, this is a positive charge right here, and this is going to be a negative charge. You see here, negative. So relative to A is going to be more attracted to B, right? Because a positive and negative actually attract each other. This is similar to when you have two magnets, you have the positive end and you want to connect it to the negative end. Those magnets are going to snap together and they're going to be drawn to each other, right? So because of this, we're going to experience a force that brings us to the right. If this were a negative and a negative, they're going to be repulsive. They're not going to be together. They don't want to be together. So you would have a force that goes this way. But because both of them are in opposite directions, or opposite signs, we're going to go to the right. Okay? This is for the 0.05 kilogram particle. If we were looking for the 0.02 kilogram particle, we would be going over here towards him. But since we're looking for the 0.05, we're going to go to the right towards him. Okay? It's all relativity. It's relative. Alright, so that solves one of the questions. But we need to find the acceleration. Whenever you think of acceleration, you have to think about the Newton's law, right? That force is equal to the mass times the acceleration, A. Alright, we have the mass of the particle, but we do not have the force. What can we use to find force? Well, it turns out that we can use Coulomb's law, right? To find the force, because the force, let's call that force Coulomb, is K times Q1 times Q2 all over the radius squared. It's important to know that this is going to be a magnitude. And a magnitude means that instead of having -5, we're just going to have the absolute value of -5, which means it's just 5, okay? Because this is a force. And if we're just asked to find the magnitude, you're just going to have positive values, okay? So that's all it means. So we're going to plug it in. One thing that you should know is that K is equal to 9.9 times 10 to the 9th Newton meter squared per Coulomb squared, right? So we're going to put that. So that's our force, okay? That means that acceleration would have to be our force, let's say Fc, that one, divided by m. Alright? So let's write it out. And the m is the mass of the particle, which is this. Okay? So we're going to write this out right here. We're going to say that we're going to have 9 times 10 to the 9 Newton meter squared per Coulomb squared. Multiply that with, what's the magnitude? It's 5 times 10 to the -6, because microcoulomb is just -6, right? 10 to the -6 microcoulombs. Now you would put -20, but we're looking for magnitude, so we're just going to put 20 times 10 to the -6. Notice that I don't have a negative sign, okay? I do not have a negative sign. Alright, so after that, I'm going to put what? I'm going to put the distance, so that's 0.5 meters, square that, and then I'm going to put the m over here. So the m will be what? It's going to be 0.05 kilograms. Notice that it has to be kilograms, not grams. I converted the units. Usually when you're doing physics, you're going to be working with kilograms, meters, seconds, right? So be careful with that. Notice that the c's cancel out. Well, this is a c, but it cancels. And the meter squares cancel as well. So it's going to be newtons over kilograms, which is, I would assume, acceleration. So if you were to plug this into your calculator, you would have 9e to the 9 over 5 -6 and 20e -6, and let's see, 0.5 squared times 0.05, right? And we end up getting 72 meters per second squared in the right direction. So the trick was that realize that the Coulomb's law is actually the force, and this could be replaced with this one. And then just solve for your acceleration. We didn't use this because we're going to solve the acceleration for A. So we used the mass of A. Alright? We're asked to find the equivalent capacitance for the circuit. Notice that each capacitor is worth 12 picofarads, and a pico is just equal to 10 to the negative 12. Alright, so that's what it is. Now, a lot of you may have been confused, but this is capacitance. It's not resistance. See, if you can realize that this circuit is in parallel, that's good. But for a parallel circuit, or for a parallel capacitance, let's call that CP, C part, is going to be what? C1 plus C2. It's the opposite. It's the opposite of the R, the resistance in parallel, where you have 1 over R tot, which is 1 over R plus 1 over R2. Alright? This can be, for the series, for capacitance in parallel, you can think of it as like what? As a resistor in series. Right? Okay. So it's kind of like the opposite. So whenever you think of, oh, this is in parallel, you're going to think of resistors, right? So you have to make sure that you know what you're looking at. This is a capacitor, and the capacitor is like the opposite of a resistor. And instead of being parallel, instead of using this equation, you're going to be using the series equation for parallel capacitors, alright? So that's what we're going to be doing in this problem. First thing I would do, right? First thing I would do is actually change my values. So instead of having 2C, C, C, 3Cs, I'm going to write it as this. This is worth 24. This is worth 12. This is worth 12. And this is worth 36. Okay. And notice that whenever I'm gonna redraw the circuit, but I'm not gonna do like lines. It takes too long. It gets messy. So I'm gonna have like an abstract, right? Like this is gonna be the equivalent, and you're gonna have to imagine like the lines right there, right? Okay, so let's get into it. First thing I notice is that this indeed is a parallel circuit for capacitors. How do we know that? How do we know that it's gonna be parallel? Well, here we go. Let's say that you're playing Mario Kart, right? And this is going to be the start. And this is going to be the finish. Okay? So, if we were dealing with series, you're going to have your start, and this is going to be your finish. If we're dealing with series, let's say that this is resistor 1, resistor 2, resistor 3. It doesn't matter, okay? It just has to be like this. Then imagine that these are going to be like checkpoints or gates. So Mario, or your favorite Nintendo character, is going to go through gate 1. He's going to go through gate 2, gate 3, and gate 4, and then he's going to hit the finish line and finish. What we had was a series of events. We had a series of checkpoints. We didn't deviate from the path. He only had one path to follow, and he went through that path. There were no secret passages, no hidden shortcuts. It was just a straight path, right? So that's a series, right? That's a series. I'm not dealing with capacitors right now. I'm just talking about series and parallel, how to find it. But let's say that you had this, right? Now this is your start and this is your finish. Alright, so now Mario, or Donkey Kong, he goes, and he can, go over here and do this, right, to finish. But the main issue is that he can go this way. Or he could go this way. Or even he can go this way. And so, do you see the problem? Is that we don't have a series anymore. Mario, or whomever, can go to shortcuts. He could go to this shortcut, this shortcut, this shortcut, and still hit his final goal. And so that's parallel. You have more than one option for a path. You're not just restricted to a straight line. You're actually able to go through different shortcuts, different pathways, okay? So that's the main difference between a parallel and a series, okay? So, how does that help us? Well, let's imagine that we were playing Mario Kart. We start, oh look, I could go here and do that. And I could also go through here and do that, instead of just going right here. That would be a series, but notice that we have two different paths that we can take, so that's a parallel. Okay, so now we're dealing with parallels, right? Whenever a capacitor is in parallel, C par, instead of doing 1 over C, you're actually going to do C1 plus C2. So it's going to be 24 plus 12. So this whole circuit is going to condense down to what? This is going to be 24 plus 12, right? So that gives us 36C, right? 36. And let's fix that 6. All right, and we still have, yeah, I'll just do the line for you. We still have that. All right. Oh gosh. All right. Let's do that. And now we want to also condense this, right? Because those are two capacitors in series. Wait. If it's in series, oh man, I'm really sorry. Sorry. So yeah, it actually is this. So yeah, you're gonna have these two right here, but when they go this way, they're actually connected, right? So you can go through a series. However, this one is going to be a parallel, right? So what I'm trying to say is that relative to this area, this is going to be series. But if you're considering both of them, this is parallel, right? Whenever you're working with this kind of problem, you're going to condense one area first, and then you're going to condense the other, and then together, you're going to condense both of them. Alright? So what does that mean? It means that, first of all, I'm going to treat this as a series. So here's how you do it. You take this one. You're going to use the C series, which is 1 over C, which is 1 over C1 plus 1 over C2. Okay? That's because when Mario drives in this path, he only has one path to take. So that's a series. Relative to the whole circuit, however, this is parallel and this is parallel. So whenever we're in this path right here, we can add it up as a series. So we're going to take, what? 24 times 12 over 24 plus 12. And again, I'm really sorry that I messed up. 24 times 12, it happens. 24 plus 12. And we end up getting 8. So that's 8. We're going to do the same thing here in a different color. So this right here is going to be 12 times 36 all over 12 plus 36. So let's see. 12 times 36 times divided by 12 plus 36. And we get 9. We get 9. Alright. So now we now have this. We now have, that's a capacitor. This is the capacitor. Right. Now, okay, we don't have this anymore, and we don't have that, right? So we're done with series. We are now strictly in what? Parallel. And whenever we do parallels, we just add them. 8 and 9 is just 8 plus 9, which is what? 17. So 17 picofarads. Alright? So the main trick here is to differentiate what is a parallel and what is a series, right? So altogether, this whole circuit is in parallel, right? But relative to this little area, when we go down to our shortcut, that's a series. When we go to this shortcut, that's a series. After we're done compressing our capacitors, we have what? We have parallel, because we don't have anything else in here. We don't have any more capacitors to add up or anything. All right. And again, whenever you're working with capacitors, it's kind of like the flip-flop, right? So a series for a capacitor is actually going to be 1 over C. But when you're working with parallel capacitors, it's C1 plus C2, right? So compress and then add together. Now, for this question, we're given that a capacitor has a 4 meter square area and a separation of 2 centimeters. We need to find the capacitance. One thing that you should know is that for capacitance, whenever you're given an area, this equation should just pop into your mind, or at least you should look at the equation sheet for it. Okay, it's going to be the dielectric times the permittivity of free space times the area divided by the distance. Notice that we're not given a dielectric. I'm just putting it here because it's pretty useful to have. Just have it there. If we're not given a dielectric, then K dot is just going to be equal to 1, right? So it's going to be ignored. Okay, so you're probably wondering what this E sub naught is. And E sub naught is actually equal to 8.85 times 10 to the, what? Negative 12 Coulomb squared over Newton meter squared. Okay, cool. That's the permittivity of free space. It just shows us the influence of an electric field. So the electric field can like manipulate charges and point charges within it, and it has this weird little constant. It's not important to know, it's just you're gonna know the numerical value for it. Okay, so we're looking pretty good. We have the area, which should be in meters, that's good. But notice that our separation, our distance is 2 centimeters. Well, what can we do? We can say that 2 centimeters is really just 0.02 meters. Alright, we now have that the capacitance is equal to, let's do 1. That's just dielectric. If you don't have a dielectric, just put 1, right? Or you could just ignore it. Times 8.85 times 10 to the negative 12 Coulomb squared over Newton meter squared. Okay, and then multiply that by the area, which is 4.0 meters squared. Divide this by what? By the distance of 0.02 meters. Notice that the meter squares cancel with the meter squared, and we're given Coulomb squared over Newton meter. Okay, so Coulomb squared over Newton meter, and what do we have? We have what? 8.85 E negative 12 times 4, right? Divide that by 0.02, and it turns out that our capacitance is very small. It's 1.77 times 10 to the negative 9. Right, you could say Coulomb squared per Newton meter. So let's double check. What was the trick? The trick was that whenever you're given area, you should instinctively think of this equation, right? You should think of that equation because it has area. It also has displacement, which is the distance. E sub naught is just a constant, which is 8.85 times 10 to the negative 12. We're going to multiply that together and then divide by the separation in meters, and we should get the capacitance. All right. In this question, we're asked to find the electric potential at point P, a distance away from the radius, from the center of the circle, right? Which is a distance of x, right? So we have a positive Q right here, and it's said to be a conducting ring. And whenever, well, yeah, let's talk about insulation and conduction. When something is insulated, the charge right here, the charge is actually going to remain inside, right? Is going to remain inside. So we have all these trapped charges inside of the container. And so these are all trapped inside. There's nothing coming out. There is no leakage, okay? There's no leakage. And whenever we're talking about a conducting sphere, that's an oval, conducting sphere, we have no charges inside. There are no charges inside at all. Actually, they're on the surface on the outside. So what does that tell you? Well, it tells me this. It tells me that if I were to do a Gaussian sphere over here, and I told you, oh, we got to find the electric field, right? We got to find the flux inside this sphere. Well, you can't do that because the Gaussian sphere is outside and it's not detecting any leakage because everything is stuck inside, since this is a conduct, right? However, if you wanted to find the flux, you would have to do a Gaussian sphere inside the small circle, right? Because that's where the charge is at. Actually, you would have to do a smaller one, right? So, if I told you to do the Gaussian, a Gauss law with this problem, you could, because the charges are outside. And it's pretty simple to do that. In this case, we have a conducting sphere, so our charges are going to be outside, right? So our charges are going to be outside. Let's just erase this really quickly. That's just a quick concept for you to do that. Okay. And so since our charges are outside, we can do positives, right? You always assume positive charges. Now, it's important to know that whenever you have a positive charge, that we are so happy and we're so positive that we radiate positivity. So we have our electric field lines coming out, and we're just happy, okay? However, when you're dealing with negative charges, you're going to have this negative. And when you're negative, everybody's attitude gets to you. You have everything coming towards you. Not good. Pretty bad. You're pretty sad. All right. And this brings us to this concept. Since we have positive signs on our surface, since we're conductors, in the previous picture, I said conductor, even though the things were inside. That's actually an insulator, so sorry. That's an insulator, not a conductor. Insulators have their charges inside, conductors have it outside, as you see here. If the charges were inside, right, then that would be an insulator. Right. So since we have our charges outside, we're acting as a conductor, and our charges are going to go outwards, right? Charges are going to go outwards. And this is important because when we do a Gaussian sphere, we want it at point P. Not really a sphere, but I don't have room. These lines actually hit our sphere at a perpendicular angle, and we can actually measure how much flux, how much the field lines pass through this surface. So that's what we're doing when we're doing Gaussian spheres. So here's how you do it. We have that E times the area of the Gaussian sphere is equal to the charge that's enclosed divided by epsilon sub naught. Alright? And we're trying to find E because, well, when we have electric potential, I know that E is equal to what? Well, it's equal to the electric potential over the distance. Electric potential is just another way to say voltage, volts, and that's right here, right? You could just say that. So if I find E, I could do this. I could do E times D is equal to V, right? So that's kind of like the game plan I'm doing. All right, so what's the area of the Gaussian surface? Well, the Gaussian surface in this case is going to be a sphere. And so the area of a sphere, which you should know, is 4 pi r squared, right? Okay. And we're just going to divide this out. So we have E is equal to the charge that's enclosed divided by epsilon sub naught. And we're going to divide it by A, right? I just moved the A over here. Okay. So we have that E is equal to positive Q, that's the charge enclosed, divided by 4 pi r squared E sub naught. E sub naught, okay? That's an E. That's epsilon. Alright. Now, this is our value, alright? We will now write that in purple. So E is going to be what? Is going to be plus Q 4 pi r squared epsilon sub naught times what? The distance. The distance from the center of the circle to point P. We're going to call that x. So the distance is going to be x times x. And so technically you found your electric potential. And I mean, it really was just a Gauss law, right? And I was just explaining to you conceptually. So the trick here was to realize that this is a conducting surface. And whenever we are conductors, we're going to have our charges outside. And that makes it very nice for us to measure the flux with our Gaussian surface, because these positive charges radiate electric field lines that can be measured by our surface, all right? Because flux is just the amount of field lines that pass through the surface. However, when we are insulators, our charges are not going to be they're not going to be outside. They're going to be inside the sphere. This one, the physical sphere. And if we're trying to measure like we're doing right now, it's not going to work because these field lines cannot escape the physical circle right here, right? They can't escape, and so they cannot be measured. The only way that you can measure that is by making a small Gaussian surface that lies within the insulating sphere, okay? For this problem, we're asked to find the circuit's equivalent resistor, right? The resistance, okay? So what do we have? We're going to start from, it's pretty random, like you don't have to start where I'm starting, but I like to start like this. Actually, it does matter. Whenever you're working with this type of problem, you're going to do the end first, right? We're going to be working from right to left. So we're going to work this way, all right? So from right to left, this is a resistor. We have ohms. And so for resistors, it's important to know that resistors in parallel are going to be 1 over R T, tot, which is 1 over R plus 1 over R2. And when you're working with series, that's going to be R1 plus R2. Capacitors are basically the opposite. If a capacitor is in parallel, you're going to be C1 plus C2. If a capacitor is in series, it's going to be 1 over C plus 1 over C2. Okay? So, what do we have here on the corner? Well, at the end of it, we can have, when we're playing Mario Kart, we have a shortcut to go this way, we have a shortcut to go that way. And so what does that mean? It means that we are in parallel. And when we're in parallel, we have to do the 1 over R, right? So we're going to do 15 times 30 divided by 15 plus 30. So if you were to put that in your calculator, 15 times 30 divided by 45 would actually be 10. So it's going to be 10, right? So we have 10 ohms. And let's write out the equivalent structure, right? Let's write out the equivalent structure. We now have the battery. And this is now condensed. Whoa. Let's see here. right? So now this is going to be 20 ohms, and this is now 10 ohms. This came from adding these two, right? With 1 over R1, 1 over R2. So we just kind of condensed it into a super resistor, right? And it's important to know that you did it right because this new resistor is less than the smallest one, right? So it's less than 15. Pretty good sign that you did it correctly, right? And now when we're playing Mario Kart, we go over here, checkpoint 1, checkpoint 2, no shortcuts, cool. So we're going to be adding it in R1 plus R2. So we're going to do 20 plus 10, that gives us 30. So for part A, it is 30 ohms for the equivalent resistance. And I highly recommend, because since we have the voltage and since we have the ohms, we can find the current. Now, it's important to know that in a typical circuit, that the current, the amps, right, the I, is constant. It doesn't change. It remains the same. So we can actually find the total current for the circuit. And here's how you do that. We call Ohm's law, that the resistance is equal to the voltage, this is the voltage, it's 9, divided by I. Alright, and we want to find the total current. So we could say that I total current, is equal to the voltage, we're going to put this over here, divided by R. So that gives us 9 divided by 30, which gives us what? 9 divided by 30 turns out to be 0.3 amps. That's pretty important. Why is that important? Well, in part B, right, it says what is the current through a 20 ohm resistor? Okay, well, it turns out that it's going to be like 0.3. Why? Well, like I said, the current is constant. The current flows through the circuit. It doesn't matter if it's over here, or if it's over here, or if it's over here. It's going to be the same current over here, right? Because the current in has to be equal to the current out, right? So we're putting in 3 amps. 3 amps has to come in. 0.3 amps has to come out, right? So 0.3 in, 0.3 out. So you can solve for the current right now. That's what I did because it makes B a lot easier. Since current is constant, then the current that goes through the 20 ohm resistor has to be 0.3. Okay? So that's part B, right? In fact, if they ask you what is your current going through a 15 ohm resistor, 0.3. Alright, cool. And and while we're on that page, if you were to have a circuit that was just filled with parallel, right? If we were just parallel and stuff, then the voltage would actually be constant. So you have 9 volts, you're going to have 9 volts throughout the circuit, but that's only for parallel circuits, okay? And you can exploit that if a question asks you for that. Just automatically know right off the bat that for volts, it's going to be constant, but only for parallel circuits, okay? It's going to be parallel. Alright, now question C asks, what is the voltage drop? So a volt drop is what? Well, it's actually equal to delta V. And when you have a delta, it just means that you're going to be subtracting. So your final volt minus your initial volt. And we have to measure it through the 20 ohm resistor. Okay, so how do I do that? Well, it's really simple. Our starting volt is going to be 9 volts because that's how much we're putting into the system, right? We have 9 volts. So all we got to do is calculate how many volts are in this 20 ohm resistor, alright? Now, because this is not completely a parallel series, because this is not a parallel completely, it has a series attached to it, voltage is not constant, so it could fluctuate. It could be different here, it could be different there, it could be different there, okay? If it's parallel, then it's going to be the same here, same there. So to find it, we just have the resistance equal to voltage times the amp, right? So we could do 20 ohms times, I'm going to have this over here, I'm going to multiply it out, Ri, so I is what? 0.3 amps. And we end up getting what? 20 ohms times 0.3 amps gives me 6 volts. That is not your answer though. That's not your answer. We will now have that 6 volts final minus 9 volts initial is going to be negative 3 volts, or simply a loss of or 3 volts, right? So our voltage drop is we lost 3 volts, and that voltage could be, you know, it can be changed into heat or electricity, or not electricity, or light, right? So we actually kind of converted 3 volts, right? So all I did here for this whole question is do this. We condensed our circuit, right? We condensed our circuit starting from the back. Party in the back, right? Business in the front. Because this is in parallel and this is a resistor, we did 1 over R plus 1 over R2, right? And whenever we condensed it, we get one super resistor. And when we're playing Mario Kart, it's just one path. So that's a series. A series is R1 plus R2. So we have 20 ohms plus 10 ohms gives us 30 ohms. Alright? And instinctively, you want to be able to solve for the whole amp for the circuit. And to do that, we just use Ohm's law, which is R is equal to V divided by I. We solve for I. So we have 9 volts divided by 30 ohms. It gives us a 0.3 amps. That amp is constant throughout the whole circuit. Okay? Right. And to calculate voltage drop is just the difference between your final voltage and your initial voltage. In this case, our final voltage was 6 volts for the 20 ohm resistor. The initial was 9 volts. So you end up losing 3 volts, right? So your answer would be 3. In this problem, we're asked to find the total electric potential at the center of the circle, right? So what is the electric potential anyways? Well, the electric potential is defined as this. It's V, which is equal to K, Q1, Q2 over what? Well, it's not R squared because that would be Coulomb's law, but rather it's just R, right? It's just R. And we're asked to find the electric potential at the center of the circle. So it's kind of like finding the total voltage for the surface, or not the surface, but for the center. So it's going to be V, right? That's just repeated addition. So it's going to be V1 plus V2 plus V3 plus V4 for the center of the circle, or for the square. All right. Well, if we're only dealing with the center, then are we really caring about the physical attraction of these two, or this, etc.? Do we really care about that? No. We only care about the attraction towards the center. And so I notice that I have a distance right here, so I'm going to solve for the distance. Alright? So what happens? Well, if we solve for the distance, it's going to be like that. And it's also going to be like this. But what I'm trying to say is, just think of a triangle, right? With a side of A and another A. And we got to solve for R. Okay? So how do I do that? Well, R is like this. It's going to be A squared plus A squared is equal to R squared. And so the square root of A squared plus A squared will give me R. Well, I don't have any numbers, so how do I do this? Just think of it as this way. if you have a squared plus a squared, then you can factor out an a squared, right? It's not intuitive, but you can. So it becomes a squared of 1 plus 1. If you were to put this back in, then you would get what you have, right? So what's 1 plus 1? Well, 1 plus 1 is 2. So we can do this. A squared times 2. A property of square roots is that whenever you're multiplying something, you can actually break the square root. So you can do this. You can do a squared times the square root of 2. Anything squared under a square root just becomes the base. So we have a times the square root of 2, right? So that square root took away my exponent. So this whole thing becomes a times square root of 2. Right. So the reason why we did that is because we're going to be doing repeated addition. We're going to do k. We will have q1 times. Now, we don't have a charge for this one, right? But we do have a charge for this. And it's going to be q3 all over. Now, what's the distance? Well, the distance is this. But we already calculated it to be that a over a times square root of 2. So it's to be a square root of 2 plus k q1. Well, not q1. It's the other one. So q2 times. Now, when you're working with voltage, we're not doing magnitude. We're not doing magnitude. So the negative sign does matter. It does matter. Okay. The negative sign matters because voltage is a scalar. You don't say, oh, we have 5 volts to the north. We have 5 volts northeast. You don't say that. You say we have 5 volts. We have negative 5 volts because it's a scalar. Okay, and so when it's a scalar, negative signs do matter. So k q2 times negative 2 q4 all over a square root of 2. Alright, and yeah, that looks pretty good. So that would be what? The total voltage. That would be the total voltage at the point. Alright? So the trick was for part A is that we're only finding the electric potential, this guy, for the point here, right? And since we're only directed at the point, we're not caring about the horizontal component. We're not caring about this part or whatever. We're actually caring about the diagonal, right? So that means that there has to be an electric field that has to pass through this point where our green dot is. And that's just a diagonal, right? So you could take this point and find the electric potential. Because the magnitude goes over here. It goes right through our green point. Okay? So we take q1 times q3 and divide it by the distance between them, and we're going to add that with q2 times negative q4. Oh, yeah. So, yeah. Just make sure you have your k's or whatever. You can also simplify it to be this. I think it's a lot better like this. It's going to be q1 times q3 minus, because of this negative sign, q4 times q2. So that could be simplified. Now we're asked to find the potential energy of the 4 charges. So this is completely different. It's completely different, all right? It's a bit longer, but when we're considering all 4 charges, we have to consider the horizontal, and we have to consider the diagonal and this as well. Okay, so what does that mean? It means this, that the repeated addition of the voltages is equal to what? It's going to be k q1 times q2 over the distance that separates them. That's going to be a, plus k q1, let's go over here, times negative 2 Q4 over the distance that separates them, A, plus what? K Q1 times Q3 over the distance that separates them, that's going to be A square root of 2. And notice that there's something special. The special thing is that Q1 appears in every system, right? It appears here, here, and here. Whenever you're doing this, you have to pick a point and make it as your mother point, right? So Q1 is going to be like the parent, and we're just going to base everything off of Q1. And this only applies to when you're finding the potential energy of the 4 charges, not of the center. The center is completely different. And that means that we can actually simplify it. We can do K times Q1, and notice that A shows up too, right? So we can say Q1 over A, multiply that with what? Q2. You can do Q2 and plus negative 2Q plus Q3 divided by square root of 2. And that would be your equivalent answer. So let's make sure that everything's right. Q1. Let's see here. Yeah, that would be correct. So that would be the total potential energy relative to the 4 charges. All right? It's relative to the 4 charges. Just pick a point right here and just do your total potential relative to that point. All right? So the trick here was that whenever you're doing potential energy at the 4 charges, you consider the horizontal, you consider the vertical, right? But when you're doing the total potential energy at the center, you're only considering the diagonals, all right? Because that diagonal brings a force, and the force goes through the dot, right? Or it brings a scalar, whichever way you want to see it. So we're asked to find the electric field of a sphere that has a radius of 5 centimeters, and the net charge is negative 20 nanocoulombs. It's important to know that a nanocoulomb is 10 to the negative 9. All right. So let's actually convert our units to the standard, right? So 5 centimeters becomes 0.5 meters, and that's about it. So first of all, it's asking us for the electric field in a 1 centimeter area, or right, for one centimeter radius. So this is a conducting sphere. And what does that mean for us? So a conducting sphere means that we're going to have our charges outside, right? So we have our charges outside, and notice that these charges are going to kind of radiate their electric field lines, and these actually radiate outside of our sphere, or Gaussian sphere. Okay, so if we're only looking at the 1 centimeter radius, then that means that we have to be like over here, right? That our radius has to be inside. And what does that mean for us? Well, if our electric field lines are outside of the surface, outside of the physical surface that we're trying to measure, then there is no electric flux. Why? Because the thing that we're trying to measure is outside and we're inside, right? Right? If you're trying to measure the temperature outside, let's say it's 90 degrees, are you going to measure it from inside the house? No, because that temperature is outside the house. Okay? So you can't just say, oh yeah, it's -5 or something. No, because there is no activity going on here or here or here or there. It's not possible, okay? It's not possible. If you were to say, oh, find the field, the electric field at 6 centimeters, then yeah, because we're in that range, we're over here, and we could find the electric field line just perfect. So for letter A, with a radius of 1 centimeter, you can't measure it because what we're trying to measure is outside, right? And we're stuck inside this area that is empty, devoid of anything. And so that would be 0 because there's nothing inside here. We can't measure it, right? That's 1 centimeter, right? Very important for you to know. If this were an insulating sphere, then our charges would be inside. And then, yeah, we can measure it. That's cool. We can measure that. But this is a conducting sphere, and our conductors have charges outside. All right. So for letter A, it is 0. Now, what about for 8, or for letter B with a radius of 8 centimeters? Well, for 8 centimeters, you're going to have to do this. Oh, first of all, we have to verify that this is correct. For 8 centimeters, let's see, 5 centimeters, this would be like 8 centimeters, let's say. Then yeah, our Gaussian surface can actually calculate how much electric flux we have because we are outside and we're trying to measure the temperature outside the house, right? So we can actually do it. This is a completely valid operation. And so because we are outside of the sphere, anything above 5 centimeters, we can measure it. If it's below 5 centimeters, we can't do it, right? So let's do it. The Gauss law is E times A is equal to the charge enclosed, Let's say that this is, yeah, they actually gave us a physical number with epsilon sub naught. Let's solve for E. So E is equal to the Q enclosed over what? The area times epsilon sub naught. That's epsilon, right? That's pretty bad. Epsilon sub naught. Okay, so let's actually plug this in. Let's plug it in. We are given that we have what? Well, when you're finding this, just do the magnitude, right? Just do the magnitude. So you have what? 20 times 10 to the negative 9 coulombs over what? What's the area of a sphere? The area of a sphere is going to be 4 pi r squared, right? So 4 pi, let's do the radius of 0.08 meters, and then multiply it by epsilon sub naught, which is 8.85 times 10. That's a 10 to the negative 12, right? Coulomb squared, Newton meter squared. All right. So if you were to plug this in, this is 20 e negative 9 divided by 4 pi. Oh, this is squared. You see that? Squared. 4 pi 0.8 squared, 0.08 squared, right? Then multiply that by 8.85 e negative 12. And you end up getting E field of about E, that's round, is equal to 28,100, right? And yeah, you should be good to go for that one. It doesn't matter if you don't have your units. For me, we have what we wanted, which is this, right? So that's how you would do that. Just the trick here was that for the first problem, it would be 0 because what we're trying to measure is outside, right? Is outside of our home, and our radius is inside, so it's not collecting any data. So it would be 0. For problem B, we can actually do it because our radius is outside and so is our charge, what we're trying to measure. And so you would use EA is equal to Q enclosed divided by epsilon sub naught. The area of a sphere is 4 pi r squared, so it's just E is equal to the charge divided by 4 pi radius squared times epsilon sub naught. And that's how you do that type of problem. So this portion of the video it goes over the conceptual process, the conceptual questions. So for number 1, it says excess charge on a conductor is always what? Well, on a conductor, the charge, you can expect it. Let's say that we have a Q, right? A Q. We can say that the charge inside is gonna evenly distribute across the surface. So you're gonna have this nice little charges, right? They're on the surface. And then we can use a Gaussian sphere to actually measure that. All right. However, for a conducting or for a insulating sphere, you have what? For an insulating sphere, the Q inside cannot escape. The Q inside stays stuck inside, right? So it becomes, we have our charges stuck inside, right? They cannot escape. So that's for an insulator. For a conductor, it's going to be outside. So for question 1, it's going to be what? Distributed evenly on the surface, right? So it's going to be C. It's on the surface. So you should know that. When a conductor is in an electrostatic equilibrium, the electric field inside the conductor is what? So again, we have a conductor. That conductor has Q. We have plus charges outside because this is a conductor. So what is the charge inside the sphere? 0, because there is no plus signs or negative signs in here, right? So it's going to be 0 because nothing is inside our sphere. When we do a Gauss surface, we can actually find the flux, but yeah, like but whatever's inside here, if we were to do a Gaussian surface, we're not collecting anything, so it would be 0. So for question number 2, the answer choice would be 0. When a conductor is in electrostatic equilibrium, the electric field at a point on its surface, right, will not be, so what is it asking? That's the main issue in these physics problems. What are they asking you? Well, whenever a conductor is in electrostatic equilibrium, the electric field will not be what? Well, the electric field for this Gaussian surface, you can do this. Here's some concept. When the electric field line radiates, it's going to hit the surface. So we're going to blow this image up. So here's our surface. It's like a wall. The electric field line hits it perpendicularly, right? So it is perpendicular to that surface, and then you can like measure it as it escapes. And it hits it at one point. That's what tangent means. Tangent means that you're going to hit something only at one point, right? So we only hit this at one point. So that's what tangent means. Tangent can be the same thing as perpendicular, right? So A and B are incorrect. And what is D? Proportional to the charge density of the surface? So yeah, it actually is. The electric field is equal to the charge divided by what? The area. You have epsilon sub naught. So it is charge density, which is sigma, is equal to Q over A. It's just how much charge is in that area. So charge per inch, charge per meter, right? So that is correct. It's not D. And E, greatest where the radius of curvature of the surface is greatest. Well, that's pretty, it's a lot to say, and it's very hard to digest. But what is it? The greatest where the radius of curvature of the surface is greatest. Well, terrible, right? So it's just saying, like, if you have like a very small peak and then like this, then like the electric field line is going to be really happy. It's going to be like, whoa, and like get crazy, right? Right. So that's all it's saying. If you have like a small radius, like a small difference in the radius, yeah, it's going to like it. So that answer choice E is not correct because we're looking for something that is false. So it would have to be C, 0, because 0 would only be for the inside. But our conductor, which has charges outside, can be measured. So our answer is not going to be 0. It's going to actually be a number. We can actually measure it. So it is not 0. So answer choice C would be correct. Now, 3 balls of very small masses are coated with a conducting material, right? And here is a question. So whenever we have a positive charge on A, what will happen? If we have a positive charge on A, positive, then the negatives electrons, like the negatives, are going to be attracted to here. The positives are going to move over here. And whenever the positives are here or over there, the negatives are going to be attracted to that positive. So because of this positive charge, let's say that there are no electrons here, this positive charge is going to attract the negativity of this sphere. And so all the electrons gather up on one side, and so it kind of swings a little. And since all the electrons are on one side, it pushes the positive particles on the other side. And those positive particles kind of do the same thing to those negative electrons on the other sphere. And so we have that A is going to pull B, and then B is going to pull C. Though C is going to be a little weakly attracted because, of course, we are inversely related to the distance, right? If you want Q1, Q2 over the distance, right, that's equal to the force. And so we could say that the force that C experiences is a little bit less because we are actually increasing our distance relative to A, right? So from A to C, our distance is greater than A to B, right? So we're going to experience a little bit of push, not as much as B though. So C would be correct. B moves towards A, right? And C moves a smaller distance towards B. Now, question 5. When a positive charge moves in the direction of the electric field, what happens? Well, when we move on an electric field, right? Well, let's just go through the answer choices. The charge has to be constant, okay? The charge has to be constant because we're actually doing work. Work is going to be equal to the negative E Q times the cosine theta times displacement. So let's make this little plate for a concept. Let's say that this plate is negatively charged, and let's say that this plate is positively charged, and we have an electron, negative. So this electron is not going to want to be in the area of negativity because it itself is negative, and so these are going to be repulsive. It's going to be shot outwards. So think of it like this. Think of the board as having a spring that's attached to this electron. When we pause the experiment, our spring is fully loaded and it has so much potential energy to shoot outwards. When we resume the experiment, our spring is going to shoot outwards and we're going to be losing potential energy and we're going to be gaining kinetic energy, right? So you can say that when we follow an electric field line, we go from high potential energy to low potential energy, right? And that's not good. Well, I mean, the analogy that I'm trying to show is that you always want high potential energy. Whenever you go from a high system to a low system, that's pretty bad, right? It's kind of like when you go from a high grade to a low grade. So you're going to have a negative work being done, right? And did we change the charge of this electron? No, the electron does not change. The electron is constant. If it's -1 coulomb, then it's going to be -1 coulomb. It's not going to change. It's not going to grow bigger. It's not going to grow smaller. So it's not A because charge is constant. The charge does work on the field. Actually, no, right? No, the charge doesn't do anything to the field. The charge is being pushed. Now, it's very important for you to know this. What is pushing the charge? Well, the electric field is the one that is pushing the charge. You could say that the electric field is the spring. So the spring pushes the electron. The electron does not push on the spring, right? Okay, so that means that the charge does not do work on the field. Okay. And so it's not C. Now question D and E. D says that we're gaining potential energy. Actually, we're decreasing potential energy and we're increasing kinetic energy. So so D is not correct. E says that we're losing kinetic energy. Actually, we're gaining kinetic energy because we're losing potential energy. So E is incorrect. And what about B? The field does work on the charge. Yes, that is correct. The electric field, which is our spring, quote unquote spring, does work on the electron, okay? So it actually propels us to the positive plate. So that does do work. And it's negative work because we're going from a high system to a low system. If we went from a low system to a high system, we're doing positive work. So now question 6 asks, charge Q sub naught has a potential energy of U when located at a point in the electric field. What is the electric potential? So it's basically, what equation is it? Well, here's what you do, right? So V is equal to what? K Q1 Q2 over R, right? You can denote it as U. Some textbooks do that. So what is this? Well, what is the electric potential? So the electric potential would be like E. I mean, it's hard to say because you've run out of letters, so we're going to use V again. So V is actually U divided by, that's an M, actually. It's U divided by Q sub naught, the original charge, the charge that we're kind of like basing this calculation off of, right? So it's very important for you to know that electric potential, so potential, is going to be equal to U times Q sub naught. If anything that you need to remember is, you just need to remember that equation, all right? Answer choice C is like reversed. Answer choice B, I don't know what a nano or micro sub naught is. I don't know what that is. A has epsilon sub naught. That's not correct. We're not dealing with Gaussian surfaces or anything. And E does not make any sense because we're not really dealing with radiuses or distances. So it's just kind of like a ratio, right? It's a ratio between the voltage divided by the original charge that we're trying to measure. So we're asked to find what is the measured difference in potential between 2 points in a circuit. That's just a really complicated way to say what is delta V. Oh, well, delta V is actually what? The voltage. Yeah, that's right. The voltage is actually what? The voltage at point A and the voltage at point B. So it's like voltage B minus voltage A gives you the voltage total. And so the measured difference, that difference is like delta, the triangle, right? Between 2 points in a circuit, it's called the voltage, right? Remember that. Now, we have a charged conductor in an oval shape, right? And we need to compare the potential, the voltage, at points A and B. Well, since we're on the same path, we're going to have the same amount of everything. We're going to have the same amount of voltage, the same amount of current, because this is called an equipotential surface. So this is an equipotential surface. And I assumed that because, well, it's a solid track. There's no breaks, there's no gaps, there's nothing like this, right? So if you're just given like this, if you're just given like an oval or like a square or whatever, you can assume that it's just an equipotential surface, right? And so when an equipotential surface, the voltage has to be the same. It has to be like 5 volts here, 5 volts here, 5 volts here, 5 volts here. If it has 6 volts right there somehow, then it is not equal because you have an area, a region where the voltage is different. So that would not be an equipotential surface. But for this question, we're going to assume that everything is equal. And if everything is equal, then the voltage at A has to be equal to the voltage at B. So answer choice B is correct. V and A would be correct. So what does an ampere hour measure? Right? Well, an ampere hour this is another equation that you need to know, is Q is equal to the amps times the seconds, right? Because an amp is actually just a charge per second, okay? So it doesn't matter if you have seconds or minutes, because we have an hour, and that hour has 60 minutes, and those minutes have 60 seconds, right? So technically you do have seconds here, you just have to multiply something out. But what I'm trying to say is, it's just time. So amp times time gives you a charge. Q is a charge. So we can say what? We can say that B is correct because we're multiplying our amps times a unit of time, right? So answer choice B would be correct. Amps times time would give you a charge. Alright, for question 10, it says fill in the blanks. Well, first of all, I want to look at the options. We have momentum. We also have charge. We'll call that Q. We have energy. And then we have mass. Mass, right? And power. Okay, well, when I'm thinking about Kirchhoff, I'm thinking about electricity, I'm thinking about watts, volts, amps, right? I am not thinking about momentum, so that's incorrect. I'm not thinking about mass, and I'm not thinking about what? I'm not thinking about power. Because power is like, what? Watts? Well, I'm sorry, I said watts before, right? But we're looking at specifically current, circuits. So circuits don't have like power, they don't have watts, they have charge and energy. And so we can eliminate a lot of the answer choices like that. So the loop rule, right? So the loop rule is an expression of what? Charge. So the loop rule states that that's a charge, that the voltages, right, that the voltages have to be equal to 0. So like V minus IR, or let's say I1 minus RI2 minus R3, whatever, etc. They have to be equal to 0, right? And so we can say that the loop rule actually measures the charge, which is, I know it's a bad way to say it, but it's like V. If you want a simple way to just know this, have you ever seen a junction box at the side of a house? That junction box has like fuses, it has electricity in it, right? And it has a lot of energy. Like, you're not going to open a junction box and just put your hand in it and like break some wires out, right? Because you would be killed. There's like so much energy flowing through that junction. And so you could say that Kirchhoff's junction rule, which is what? That the summation of the amps in has to be equal to the summation of the amps out. And yeah, you're not going to touch a junction box because half an amp can kill you, and it's going to kill you. Half an amp is going to kill you. And so you can think of that a junction box which has a lot of amps is going to kill you because those junction boxes carry a lot of energy. So if you just know one of them, then you know the other. V has to be equal to the charge. So Kirchhoff's loop rule explicitly explains the conservation of charge, while the junction rule explains energy. So the trick here was that whenever you see a junction box, you just think of energy. Kirchhoff's junction rule deals with energy. That means that Kirchhoff's loop rule has to be with charge, right? So for our bonus question, a wire with the resistance of R is stretched out to 5 times its original length. In terms of the original resistance, the new resistance is what? Well, you're going to have to realize that you have another equation to remember, that resistance is equal to the resistivity, rho, times the length, times the area, right? So it's not very intuitive, but let's see here. The area, well, actually we're dealing with a, what? With a wire, and wires are actually cylindrical. Here, cylindrical. So some wire, it's a pretty bad wire. It's really bad. So that's a wire. And we're going to extend it. It's important for you to know that as you increase the length of a wire, right? As you increase L, your resistivity, your resistance is going to increase. So we can eliminate answer choice A, and we can eliminate answer choice C, because those C stays the same and then A decreases. That doesn't make any sense. But now you have to realize that we're not going to be focusing on what? The length. We're going to be focusing on the circle itself. So what's the area of a circle? It's 4 pi r squared. Okay, that's the area of a circle. And since this is a cylinder, we're going to multiply that area times the length, right? So you can imagine little circles, really infinitesimal, whatever, the smallest circles ever is going to be multiplied by the length, and so you get like the cylindrical effect. Infinitesimally small circles, thin. So we could replace r with rho times, let's say we're increasing the length by 5, so we're going to say 5L. Our area is going to be 4 pi r squared L, right? So these L's cancel out. So that r is equal to rho 5 over what? Over the area, so let's say A, because this is just like the area of a circle, right? So you should know that as you increase, realistically, in real life, if you were to get like a very thick wire and just stretch it out, the circle would actually decrease, right? So if you increase it by 5 meters or whatever, you're decreasing the area of that circle. Here was the original circle. Now you're decreasing that circle, decreasing because you're stretching it out. The material has to spread out, so the area would have to be thin. So it would be what? You're dividing the area by 5. So whenever you're dividing something, you can multiply it by the reciprocal. So r becomes rho 5 times 5 over A. So what does that mean? It means that our resistivity is going to increase by 25. Again, it's not a very good problem. I don't think it's common. I don't think you would expect to know how to do this, right? So it would be D, 25 resistance. You're actually increasing the factor by 25, right? So it brings us to the last question. When the potential difference between the plates of a capacitor is doubled, the energy stored in the capacitor is what? Well, when you're thinking about charges and distance, right? Or charges and voltage, you should think of this: the charge divided by the voltage, which is the potential difference, is this equation. So let's see here. Well, we're keeping charge constant, right? We're keeping like 5 coulombs, and we're not changing it. So whenever something is remaining constant, you could just put a 1, right? And now you're actually, what? You're doubling the difference. So V2, or delta V times 2. And really, it just gives you this, 1/2. Because that V is multiplied by 2. So instead of having C where it equals to 1 over 1, you now have C is equal to 1 over 2. And so it means that our capacitance is going to be halved. And it makes sense. The more you increase your delta V, the smaller your capacitance is. So it's not A, because A increases capacitance. That's not good. B is also incorrect because you're increasing capacitance. C is incorrect because you're increasing capacitance again. And D, you're not increasing capacitance, you're increasing voltage. And D is incorrect because, well, algebraically, if you increase the denominator by a factor of 2, you're effectively cutting it in half. So answer choice E would remain the correct answer. Again, I hope that this really helped you out for your upcoming exam. If you need any more help, just do a lot of practice problems. That's what I do. And just study hard, right? So again, I hope that this video helped you, and I hope you do well on your exam. Thank you for watching.